Hello, my name is Alberto Gascón, and I will be speaking on behalf of the Electromagnetism Group of Granada about a new meshing tool for efficient conformal FDTD simulations. In a FDTD simulation, we face the following problem, and is that the time stability condition sets that the maximum time step allowed for the simulation depends on the smallest area on the FDTD cell. This might pose a huge efficiency problem since if we have a geometry with a very small area, this means we are going to have to use a very much small time step. Our proposed solution is a new meshing tool, which we have called the AMesher, which is able to generate meshes that allow to run more efficient FDTD simulations. Its main feature is that it deforms the original geometry so that it would cross the edges at certain user-defined regions only, avoiding small FDTD areas on the cell. But at the same time, it preserves the main features of the geometry. It provides a trade-off between the adaptivity of the geometry and the restrictions on the stability limit. And we will show the key points of the measure using this cylinder as an example. The measure has three modes. The first mode is the raw mode. And in this mode, the triangle of the original mesh is sliced using the grid planes, resulting on a collection of triangles that fulfill two conditions. First, that every triangle belongs to one and only one FDTD cell. This means that no triangle crosses any subfaces, and also that it respects very faithfully the original geometry. Here on the right, you can see the top view of the cylinder, and you can see the resulting mesh. But the problem is that this mesh, as you can see on the close-up on the top right, still produces very small FDTD edges. So we are still going to have the constraint on the maximum allowable time step. This problem can be partially improved using the adaptive mode. In the adaptive mode, the triangles of each cell resulting of the raw mode are analyzed to find set of triangles which can be deformed while preserving the main features of the geometry. The main features are the corners of the geometry, the contours in the case of open surfaces, and something we have called the edges. And an edge is a frontier between two flat surfaces that form an angle above a 13 threshold. As you can see here in this example, the top side of the cylinder and the lateral side of the cylinder should be treated as distinct surfaces that cannot be collapsed. And this, the edge of the top of the cylinder is going to be considered an edge. Here you can see the top view of the cylinder, and where you can see the result of the adaptive mode. The original geometry has been significantly smooth and reducing the number of triangles. And since a lot of small triangles will be merged into equivalent larger triangles, the possibility of having a small FDTD edges is greatly reduced. However, it's not completely eliminated. And as you can see here in the close-up, we still have some edges where there are very small FDTD edges. This can be solved using the snapped mode. In the snap mode, the vertices in an edge are snapped, which means to move to a certain from a certain for from a region considered forbidden, which is set by a certain forbidden length, which is user defined, to a valid point. And the valid points are always the cell corners and a series of edge points, which are a number of user defined points in the non-forbidden region. Here on top, you can see there are only three valid points, which are the corner and the edge point, because everything is considered forbidden except for the center and the corners. And here on the bottom example, you can see that the forbidden length is something like a fifth of the edge, and we have three valid edge points in between, plus two cell corners. We have five valid points, and any point crossing the edge will be moved to the closest valid point, and thus avoiding having very small FDTD edges. Here you can see the top view of the cylinder in the snap mode. You can see there is an improvement from the adapted mode, and the very small FDTD edges have disappeared. Here you can see an example of a bit more realistic case. This is a bow tie antenna This is the mesh in GID, and this is the resulting remote mesh. As you can see, all triangles belong to one and only one cell, but we have some very small FDTD edges. Here you can see the adapted mode, and in which, while preserving the geometry is very well preserved. The triangles are the mesh is way simpler. There are less triangles, and there are no small FDTD edges. This measure has been integrated in GID, and once selected, a series of problem-specific options pop up. So we have from top to bottom the measure options, the selection of the bounding box, the selection of the grid, and the selection of a series of user-defined materials. If the meshing options button is selected, we the program shows this selection menu in which we can select between the different meshing modes, the raw, the adapted, and the snapped. To select the raw mode, both boxes, the collapse internal points, which is a selection for the adapted mode, and the snap box should be unchecked. To use the adapted mode, the collapse internal points should be checked and the snap unchecked. And to use the snap mode, both boxes should be checked. While using the snap mode, we have two further options: the forbidden length, which sets the length of the forbidden length on the edge of the zone, and the number of points in the non-forbidden length. As for the grid selection, if the grid selection button is clicked, this menu is shown, and we have two choices for the grid selection. We can use a user-defined grid selecting the number of cells and the step size, and that's for a uniform grid. And if we want to use a non-uniform grid, a grid from the file in JSON format can be used. So to wrap up, the AMesher provides the capability of generating meshes to run FDTD conformal simulations, avoiding inefficiently small time steps. How? We have different meshing modes that allow for different degrees of mesh information. The adapted mode reduces significantly the number of triangles in the mesh while preserving the defining features of the mesh, and reduces the possibility of having very small FDTD edges. And the snap mode permits a fine-tuning of the forbidden and allowed zones for FDTD points. This means that we can we, we can ensure that there will be FDTD edges no smaller than a certain length, and this way we can set a um, we can ease the restriction on the global time step for the simulation. And this new measure has been integrated in GID as a new problem type. And thank you very much for your attention.